Welcome to Pharmaceutical Calculations, a conceptual approach, lesson 1, accuracy and precision of measurements. We have three objectives to cover in this lecture. The first one is the basic characteristics of measurement. The second one is to describe quantitatively the concepts of accuracy and precision of measurements and use these concepts to accept or reject compounded products with respect to drug dose. Now, the most commonly used property of drug or excipients is the mass, and we usually measure the mass on a prescription balance or an analytical balance or a scale. Now, we need to briefly define the sensitivity requirement of a balance if we are to understand the concepts of accuracy and precision. So the SR of a balance is defined as the smallest perceptible weight that can be measured by the balance. Anything less than that will not be sensed by the balance. Unlike integer numbers, which are exact, measurements are not exact. Each measurement is composed of a number, a unit, and an uncertainty in that measurement. For example, if you are measuring the mass of a drug, the actual measurement is the mass of the drug measured on that balance. The unit could be grams, milligrams, micrograms, nanograms, etc. And the uncertainty in the measurement ideally should be equal to the SR of the balance. So let's take a look of how do we perform measurement. Every time you perform a measurement, assuming that you are asked to measure a 100 milligram tablet, that's the true value here, on a balance of sensitivity 6 milligrams. Every time you measure the mass of that tablet, if you are trained well, the actual measurement should be between 94 and 106 milligrams. It should be plus or minus the sensitivity requirement. So the actual measurement of the drug is basically the true value of the tablet plus or minus the SR of the balance. The SR of the balance is the maximum potential error. It's called potential error, meaning that it doesn't have to incur with a measurement. Of course, you don't see it, but it is included in the final value of the actual measurement. So you may not be able, you may place the tablet on a balance. You may not be able to measure exactly 100 milligrams. Your balance may show 96 milligrams or 102 milligrams. That's because of the sensitivity requirement of the balance. That's the uncertainty in the measurement. And of course, the units here is milligrams. Now, how do we report measurements? Suppose you measure a 100 milligram tablet, that's the true value, on a balance of SR 6 milligrams 5 times, and you have to report your measurements to your supervisor. These are the 5 measurements of the same tablet. This is what I meant before. Although the true value is 100 milligrams, your second measurement just registered only 70 milligrams. The average value of these 5 measurements is 80, and plus or minus 16, that's the standard deviation of your measurements. This has nothing to do with the SR of the balance. This has to do with the analytical formula you've used to determine the spread of data about the mean or average value. So how do we report the best estimate of a collection of measurements? We report that as the average value, accompanied by a statistical uncertainty, which is the standard deviation in this case, and of course the units. So this is what we have here. The M, of course, that's the mass of the drug, and it is the reported measurement. The 80 milligram is the average value, and you have to report plus or minus 16 milligrams. Okay, so that's the units. So this is how we report a collection of measurements. I repeat, the standard deviation is unrelated to the SR of the balance. It is related to the statistical analysis, the kind of analysis you perform on these 5 measurements, in this case assuming normal distribution. Let's now proceed to the qualitative definition of accuracy and precision, since both of these concepts are related to the uncertainty of individual measurements. Accuracy refers to how close is the average value to the true value. So we compare average value to the true value, that's accuracy, okay? Precision, on the other hand, refers to how close measurements are to each other, not to the true value. Now, perhaps a lot of us have seen this picture many times, and it's very informative and very useful. Now here our true value is the bullseye, okay? So the center of that circular target. The bottom right panel here shows accurate and precise measurements, because you can see that all of them are within very close to the bullseye, the true value, and the deviation of each other is very small. That's why they are precise. The top right panel reflects measurements that are precise because they're very close to each other, but their average is far away from the true value and therefore they are inaccurate. The bottom left panel here shows measurements that are imprecise, definitely, because the deviation from each other from those 5 darts is way big. But it just happened that when you take the average of these 5 values, the average value is equal to the true value, and therefore these measurements are classified as accurate. And of course, the top left panel shows samples or measurements that are both imprecise and inaccurate. Inaccurate because their average value is not close to the true value. Okay, so this is very useful, but as a pharmaceutical scientist or as a pharmacist, you need a quantitative definition of accuracy and precision in order to use these definitions and classify your samples or formulations or measurements as acceptable or not with respect to the drug dose. So let's proceed to the quantitative definition of accuracy for a collection of measurements. For a collection of measurements, they are considered to be accurate when their average value lies within 1 SR from the true value. And you can see it over here. If the SR is 6, if your average value is between 94 and 106, the collection of these measurements is considered to be accurate. Not individual measurements, but the collection as a whole, okay? For an individual measurement now, if the difference between the true value and the actual value is less or equal than 1 SR, then that individual measurement is considered to be accurate. The quantitative description of precision now for a collection of measurements. We know that precision is referred to how close the measurement is to each other, right? So if the maximum value, if the difference between the maximum value and the minimum value is less than 2 SRs, then the collection of measurements is considered to be precise collectively, you know. For an individual measurement now, if the actual value, the actual measurement, minus the average value of the collection of measurements is less or equal than 1 SR, then that individual measurement is considered to be precise. So again, notice that precision refers to the average value, not necessarily the true value, okay? Let's take a look of example 1.3 to apply the quantitative concepts we've learned right now using numbers. Sometimes it's very helpful applying numbers. So here we have 4 groups of students, group II, IP, AI, and AP, that they were asked to measure the mass of 5 tablets. The true mass of these tablets was 100 milligrams, and you can see the true value as the thick line here, okay? Those are the 4 groups. The balance has an SR of 6 milligrams. Their measurements are the empty circles. These are their measurements, okay? And the average value is written here is the dashed line. So the average value of these 5 measurements for this group is 80, for this group is 79, for this group is 79, for this group here the average value is 100, average also, and for this group also. So let's take a look and classify the measurements of these 4 groups as accurate or precise. So in the first group, II, the average value is 80. So the difference 100 minus 80 from the true value is 20. That's bigger than 6 milligrams, and therefore these measurements are inaccurate. They are also imprecise because the maximum value is 100. The minimum value is 60. That's 40 greater than 2 SRs. Therefore, these measurements are both inaccurate and imprecise. The second group, IP, the average value is 79. 100 minus 79 is 21, bigger than 6. Therefore, these measurements are inaccurate. They are, however, precise because the maximum value is 83. See here? That's 83. The minimum value is 75. Difference is 8, less than 12, therefore they are precise. So they are inaccurate but precise. Doesn't make much good though, right? Because they're far away from the true value. The third group, AI, the average value is 100, identical to the true value, and therefore these measurements are accurate. They are imprecise, however, because the biggest value is 120, the smallest value is 80. That's 40 greater than 2 SR, therefore imprecise. So notice that here the collection of measurements is classified as accurate, but 4 out of these 5 measurements are unacceptable. If this was a drug dose, you would be overdosing the patient here and you would be underdosing the patient in the other 2. Only one of the measurements is acceptable actually. The last group, AP, we have an average value identical to the true value, so therefore the measurements are accurate, and they are also precise because the biggest value is here 104 and the smallest is here, maybe here, which is 96. So 8 milligrams less than 12 milligrams, and therefore precise. So this group has done a very good job. Why do we do this? Of course, we want to be able to prepare accurately doses for patients. And as we've seen, measurements that are collectively accurate but imprecise are not acceptable because it could just happen that most of the measurements are way off the true weight or the true mass of the drug. Of course, in the next lecture, we are going to learn how to choose the right balance to fill the compounded prescriptions within a maximum allowable error, or alternatively, we're going to learn how to calculate the least allowable weight of a drug dose within a maximum allowable error specified by the FDA and prepare our prescriptions or fill our prescriptions. But prior to that, it is important to work out the couple of problems that I've included at the end of this lecture, and try not to look at the answers before you actually attempt the problems. And perhaps we can just solve one together here. A precise measurement is always accurate. That's definitely false because the definition of precision refers to how close are measurements to each other and not necessarily how close it is to the true value. And of course, B is also false, right? We've seen it already. Of course, this is false because it could just happen that that precise measurements can have an average value very far away from the true value. Only precise measurements are accurate. That's false also. Only measurements that have exactly the same value are precise. That's true, definitely. If they don't have to be close to the true value, but if they're close to each other, they are definitely precise. Measurements that have exactly the same value are accurate. That's the F here. That is false. We've seen that the definition of accuracy refers to the average value with respect to the true value and not how close are to each other. Precise measurements, let's go to G. Precise measurements have values very close to each other, even if none of them is near the true or correct value. Of course, that's true. And the last two, inaccurate measurements, have values very close to each other, even if none of them is near the true or correct value. That's false, because we have just said many times that accuracy refers to how close the average value or the actual measurement is to the true value, not how close are to each other. Okay. Well, at this point, I would like to thank you for your attention. Until next time. Thank you.